Having known about the fully controlled switches and their characteristics, let us try to look at DC to DC converters. These are converters which are used to interface, power electronic converters which are used to interface DC voltage sources with loads, but the loads require DC voltages at levels other than the input voltage. It could be more or less. For example, you can have a 100 volt DC source, whereas your load requires only 5 volts. And these converters essentially are made of switches, inductors and capacitors like any other power electronic converter. And these switches could be fully controlled switches like MOSFETs or IGBTs, or the switches could be diodes. However, there should be at least one fully controlled switch in the DC-DC converter. And what are we interested in? We are again interested in steady state waveforms. So the steady state analysis of these converters, analysis under periodic steady state. And when we imagine a DC to DC converter, our input voltage is anyway constant, which is given. So we should produce an output voltage which is ideally like this, like a straight line. The variation of output voltage with time should be constant ideally. And of course, the output current will also be constant, because in DC circuit, the load that you have is only a resistor. And we also want to draw constant current from the input source, because input voltage is constant. So only the average value of input current will contribute to net energy transfer. So we'd like to reduce the ripple, or ideally we don't want to have any ripple in the input current. These are the ideal characteristics that we desire, ideal waveforms of a DC to DC converter that we desire. We also desire that the converter should have low losses or zero losses and so on. And another interesting point about DC-DC converters is that the average output voltage, VO average, could be less than the input voltage, or it could be more than the input voltage, or you can have a DC to DC converter which can give an output voltage whose average value is either more than the input voltage or less than the input voltage. And there are also DC to DC converters which can give a negative voltage at output for a positive input voltage. All these kinds of DC-DC converters are possible. And also, the output and input can have a common ground. That means you have one node which is common to the input as well as output. For example, you take this circuit. In this circuit, this is a power electronic converter. So it has inductors, switches and capacitor. But if you look at the negative node, it is common to both input and output. This is one type of DC-DC converter which is known as non-isolated DC-DC converter. It means the output ground is not isolated from the input ground. Whereas DC-DC converters like this are called isolated DC-DC converters, where the output and input have different grounds, can have different grounds, and this is achieved by inserting a transformer within the converter. So you have a switch, you have another switch on the secondary side of the transformer, and there is a capacitor. So this whole thing, the two switches plus transformer plus capacitor, comprises of the DC-DC converter now, and this is known as isolated. This type of converters are known as isolated DC-DC converters. And one advantage of these isolated DC-DC converters is that the input and output are isolated, they don't have common ground. That is one advantage. The other advantage is that you can have this turns ratio designed appropriately, N2 by N1. The turns ratio of the transformer can be chosen appropriately so that we can achieve very large or very small ratios of output to input voltage. So VO average, VO and Vin can be much larger than 1 or can be much smaller than 1. For example, you can, if you have a 200 volts or 300 volts input voltage and you just need 2 volts or 3 volts, this kind of converters are more preferable. than the non-isolated dc-dc converters. Since we want to analyze the converters in periodic steady state, it is good to know what all we do as a part of this analysis. First, we make certain assumptions. What are those assumptions? We assume that the switches are all ideal to start with. The non-idealities can be incorporated later. And what are the non-idealities? Finite voltage drop when the switch is on, and finite switching transition times, and so on. Similarly, we assume that the inductor is also ideal. That means it is just a pure inductor. Whereas in reality, there will also be a small resistance because inductor is made of copper wire and iron core. So there is a resistance of this copper wire. So the winding resistance of inductor we can neglect to start with. And again, the capacitor will also have something called ESR, as explained earlier, the equivalent series resistance, that can also be neglected in the initial analysis. Then all these non-idealities can be incorporated one by one or can be incorporated together. And we also have some certain approximations that are done to make our analysis method easier. What are those? The approximations are known as small ripple approximation. That means, see, we are interested in DC voltages. We are interested to produce DC voltages across at the output terminal of this DC to DC converter. So if we have a voltage across the capacitor, and typically there will be a capacitor in the output voltage because we want to produce a smooth output voltage. So the voltage across this capacitor, even though it is time varying, we assume that the ripple component of this capacitor voltage is very small compared to the average value. That is what we mean by this Vc is equal to Vc average. So that is one approximation, the small ripple approximation on capacitor voltage. The second approximation is again a small ripple approximation on the inductor current, the current flowing through an inductor. When the current flowing through an inductor is continuous, this approximation can be applied under certain conditions. What are those conditions? When the peak to peak ripple is very small, or the value of inductance is such that the peak to peak ripple in current is very small, we can apply the second small ripple approximation, that IL is equal to IL average. In fact, an approximate symbol would have been better. And then what are the principles that we use to do this analysis? So we have certain assumptions, we have certain approximations, and then what are the methods? The principles are, of course, KCL and KVL. So we know the switch state combinations and we apply KCL and KVL. So we get the expressions for the quantities of interest, and then we apply the principles of periodic steady state. So volt second balance across inductor, that we know. We also know that amp seconds or charge is balanced across a capacitor, and in some analysis the power balance, input power is equal to output power, because we are assuming the system to be lossless, the converter to be lossless. So the input power being equal to output power can also help us arrive at certain expressions easily. And when it comes to the isolated DC-DC converters, like converters involving transformer, we have volt second balance across each transformer winding, and also the flux continuity. That means the flux in the core cannot have discontinuities, so which requires infinite voltage, because d5 by dt is the induced EMF. So flux continuity principle can be useful in the analysis of isolated DC to DC converters. So here is the method, which is exactly the same that was followed for the analysis of diode rectifiers. We know the states of switches, on or off. So in case of diode rectifiers, we were determining the states of switches, whether the diode is on or off and so on. Here the states of switches are given because they can be anything based on the way we are switching. The user decides how to switch, how to turn on or which pattern to follow to turn on and off a given switch in a dc-dc converter can be chosen by the user. So we know the states of switches, they are given to us. Now that we know whether it is on or off, we just write the circuit in those state combinations. State S1 is on, S2 is off, or S2 is on, S1 is off. So we write appropriate circuit in that state and write KCL and KVL and apply principles of periodic steady state, because we are all concerned about average values in this DC-DC converters. So the average voltage across inductor is equal to 0, or the average current through the capacitor equal to 0 will be very useful. And once we know the voltage and current waveforms of interest, then we can go for analyzing the certain waveform measures that we have already defined, or we can also use these idealized waveforms to estimate an approximate power loss given the switch characteristics. So that is how we carry out the steady state analysis of DC-DC converters.